an example here of a Newton's law problem. So let's say that we have a jet aircraft. So this is going to be a jet aircraft. Let's say it's right here in the Fort Worth area. So this is going to be a fighter jet taking off over here at Carswell, the Naval Joint Reserve Base. So it's going to be a Navy fighter jet. And let's say that the mass of the jet is 23,600 kilograms. It's going to be on a training flight. It's going to be fully loaded. And let's say that the engines on the jet have a thrust of, let's say the thrust is 54.2 kilonewtons. Let's say that this jet requires a minimum airspeed. So the slowest it can be moving when it takes off is 85.0 meters per second. So I want to know if it starts off on a calm day, there's no air blowing, and it's starting from rest at one end of the runway, what is the shortest length runway that it takes for this jet to take off starting from rest? Okay. Well, it's pretty straightforward. X equals x naught plus v naught t plus 1/2 a t squared. We can put our origin at the beginning. I said it started from rest, so this is going to be 1/2 a t squared. So all we need to know is t. Well, the velocity is v naught plus a t. Well, gosh, we know how fast it's moving when it takes off, and so well, we need to know A now. Well, we know F equals MA, so A is going to be F over M. Okay, so now we can find A, we can solve for T and plug into the other equation. Okay, or we could actually just skip the whole step of solving for T separately, solve for T now. T equals V over A. If I take this and plug in there, then x is going to be equal to v squared over 2a. And so then we don't have to do that intermediate step of numerically solving for t. So all we got to do is find a. So a is going to be f over m. So that's going to be 54.2, so that's 54,200 newtons, divided by, so 54.2 kilonewtons, divided by 23,600 kilograms. So A comes out to be 2.29 meter per second squared. So I plug that into the other equation. So x equals 85.0 meter per second squared, divided by 2 and 2.29 meter per second squared. So x comes out to be 1580 meters. Okay, so 1.58 kilometers. So that is really close to 1 mile. And so that's really close to 1 mile that it takes from rest until it is able to achieve airspeed and then rotate and take off. Okay. All right, well, let's just take the same jet. Okay. And let's say that this jet, I remember I said it was a naval jet, so let's put the jet now on an aircraft carrier. And let's say it is a distance of 92.5 meters from the bow of the ship. And so I want to know, again, let's make this simple. If the ship is sitting still, so the velocity of the ship is 0, and the aircraft takes off from rest, how fast is it moving if all it does is throttle up the engines and go? Because that's what they did in World War II. They would just throttle up the engines and roll down the aircraft carrier. And so how fast is it moving when it reaches the bow of the ship? Well, that's pretty straightforward. We know that V equals V naught plus AT, okay? And so V naught is 0. And so A, well, this is the exact same jet as before. So A equals F over M. So that's 2.29 meter per second squared. Okay, so what about T? Well, we know that x equals x naught plus v naught t plus 1/2 at squared. Okay, if those are 0, then x is going to be equal to 1/2 at squared. So t is going to be equal to square root 2x over a. So that's going to be equal to square root of 2 times 92.5 meters divided by 2.29 meters per second squared. So it takes 8.99 seconds to reach the bow of the ship. So the velocity is going to be 2.29 meters per second squared times 8.99 seconds. So the velocity is going to be 20.6 meters per second. That's nowhere near minimum airspeed, so the jet just splashes into the water in front of the carrier. Okay. Well, this was actually a problem they had in World War II, is you still did not have minimum airspeed when this happened. And so you still had an issue. So what they did was, in World War II, the aircraft carrier was moving. And so that actually added velocity here. Okay, and so that would make this a little bit bigger. And then if you had a wind going this way, then the relative speed of the aircraft relative to the air was higher. And so that would add even more to here. Okay, but that's nowhere near enough to achieve 85 meters per second. It was sufficient so that in World War II, the planes that they had then, which did not have to be going as fast to take off, were able to achieve minimum takeoff speed. They still could not normally take off from a stationary aircraft carrier just sitting there. So what it would do is that they'd have the carrier moving, they'd pick up speed, they'd turn into the wind, and that would make it easiest for the aircraft to be able to take off. Okay, so what do we do? Well, obviously this is not how aircraft take off from an aircraft carrier. So what actually happens is that you have the aircraft here and you have a catapult. And so you have a high power catapult, and a little arm comes up behind the front gear and pushes on it. And so the force here is going to be a combined force. You have the force of the engines plus the force of the catapult. And that is what's pushing on this. It's not just the engines. So I want to know, how much force do you have to have from the catapult? Okay, well, F equals ma. So this is total force. Now, I should point out, when I said F equals ma, what I really mean is total force equals ma. So the total of all the forces. So that's why I'm saying that F is Fe plus Fc. Okay, so if I have to find the A. So what I have to do now is I have to find the acceleration. Okay, well, we know that x equals 1/2 at squared. We know that v equals at after we've canceled out all the stuff that's equal to 0. So we don't care about the time anymore, so this is v over a. So I plug in here, so x equals v squared over 2a, so a equals v squared over 2x. So a is going to be 85 meters per second squared divided by 2 times 92.5 meters. Okay, so the acceleration now has to be 39.1 meter per second squared. So the force is ma, so that's 23,600 kilograms times 39.1 meter per second squared. So the force comes out to be 923,000 newtons, or in other words, 923 kilonewtons. Now this is equal to the engine force plus the catapult force. So the catapult force is total force minus the force to the engines. So it'll be 923 kilonewtons minus 54 kilonewtons. And so that comes out to be 869 kilonewtons. Well, notice that the engines do almost nothing to help the aircraft take off. So that means that your naval aviator sitting here is sitting on an aircraft that knows that this aircraft cannot possibly take off on the aircraft carrier. It is thrown off the aircraft carrier. All the engines are doing is when you rev them up, keep it going once it gets off. Now, can contrast this to China's new aircraft carrier. They actually don't even achieve minimum airspeed. So they actually have a ski jump on the front. So the aircraft comes down here, and when it leaves the front of the aircraft carrier, it's actually not even going minimum airspeed. So it goes to a parabolic arc, falls back down, and then on the fall back down, it's picking up the airspeed it needs to like pull up and fly without crashing into the ocean. Okay. Back to the American case. You've got the pilot or the aviator sitting in here. Gravity is pulling downwards with a force mg. There has to be a force forward on the pilot, okay? The force forward on the pilot, okay, in order to accelerate this way. Well, how much of a force? Well, that force has to be equal to the mass times the acceleration. Well, notice this acceleration is 39.1 meters per second squared. That's approximately 4 times g. So we would say there's 4 g's of force, or 4 times the weight. So in other words, as this person is sitting here, you know, the way you experience the force is that the seat is pushing up on you with a force that exactly balances the downward force. That's why as you're sitting somewhere, you don't go crashing to the ground, because the seat is pushing up on you equal to your force. Remember, sum of the forces equals ma. So if a is 0, the sum of the forces is 0. Obviously, gravity still works on you when you're standing or sitting, but the ground or the chair is pushing up on you. And so what that means is the total force is going to be this way, which is going to be 4 mg, and there's going to be a force this way equal to mg. So that means the total force on the aviator is the square root of 4 mg squared plus mg squared. So the total force is going to be actually equal to a little bit more than that. So the total force is going to be equal to 4.1 mg. Okay. And it's going to be directed at an angle of 14 degrees, if you really work that out. Okay. What does that feel like? Well, the force is now this way, so it suddenly feels as if this guy is laying on his back with 3 of his colleagues of equal weight sitting on top of him. Okay, so that's how it feels as this jet is taking off. Okay, so that gives, this is an example of application of Newton's laws.